Ever wondered what truly powers your digital world? That unseen engine humming beneath the surface of every task you perform? Imagine a place where raw computational power isn't just a commodity, but a finely tuned instrument meticulously crafted to meet an astonishing array of demands. This is the realm we're about to enter, a landscape sculpted by innovation, where silicon artistry translates directly into your ability to create, compute, and connect. We'll embark on a journey that begins with the fundamental building blocks of modern computing, the very brains of our devices, and progressively ascend to the pinnacles of performance. Think of it as a grand tour, from the diligent, everyday assistant that handles your essential duties with grace, to the multi-talented powerhouse capable of juggling complex creative endeavors and immersive digital experiences simultaneously. Along the way, we'll encounter specialized marvels designed for specific cutting-edge applications, and then finally the titans of the industry, machines built for tasks so immense they redefine the very concept of computational scale. This isn't just about understanding how a computer operates, it's about appreciating the ingenuity and foresight that goes into designing these incredible pieces of technology and how they in turn empower us to achieve more than ever before. Get ready to peel back the layers and witness the incredible diversity and capability packed into these remarkable components, each playing a crucial role in shaping our digital present and future. At the very core of every device we interact with daily, from the pocket-sized communicators to the most powerful calculating machines, lies a pivotal element, the central processing unit. Navigating the vast landscape of available options, however, can present a significant hurdle when trying to grasp the subtle distinctions and variations between different models. Within this extensive guide, we aim to demystify the world of these integral components, delving into their unique attributes, practical uses, and the profound influence they exert on our everyday experiences. Whether you identify as an enthusiastic player of digital games, a dedicated creator of digital content, or a user who simply navigates the digital realm for essential tasks, possessing this knowledge will empower you to make more discerning selections and fully harness the capabilities of modern tools. Ultimately, comprehending what drives the devices we rely upon is the foundational step towards mastering the digital domain. This journey is not merely about dissecting the internal workings of computing systems. It's about recognizing the remarkable inventiveness and strategic planning embedded in the creation of these astonishing technological marvels, and how they in turn equip us to accomplish feats previously unimaginable. Prepare to explore the intricate details and witness the astonishing variety and potential contained within these extraordinary components, each indispensable in defining our current digital landscape and shaping what is to come. As we move beyond the foundational understanding, we'll begin to explore the tangible differences that set these devices apart, focusing on the foundational building blocks that enable everything from rapid communication to complex scientific simulations. The evolution of these crucial silicon brains has been nothing short of revolutionary. Initially, they were rudimentary, capable of only basic arithmetic. Today, they are sophisticated marvels of engineering, capable of executing billions of operations per second. This exponential growth has directly fueled the rapid advancements we see in all areas of technology, making once futuristic concepts commonplace. The sheer density of transistors packed onto a single chip, measured in the billions, is a testament to the miniaturization and precision achieved by manufacturers. This miniaturization not only increases raw power, but also improves energy efficiency, a critical factor for portable devices. Understanding the architecture of these processing units is key to appreciating their performance. Concepts like cores, clock speed, and cache memory, while technical, are fundamental to discerning how quickly and efficiently a device can handle tasks. More cores generally mean the ability to multitask more effectively, while higher clock speeds translate to faster individual operation execution. Cache memory acts as a high-speed temporary storage, reducing the time the processor spends accessing slower main memory. These interwoven elements collectively determine the overall responsiveness and capability of any given device, influencing everything from application loading times to the fluidity of complex visual rendering. The journey of these processing units began with a singular focus to execute instructions as efficiently as possible. Early iterations were characterized by a limited number of processing cores and relatively modest clock speeds. The primary problem they solved was the fundamental requirement to perform calculations and manage data flow. Created by visionary engineers driven by the desire to automate complex tasks, these initial designs represented a monumental leap from mechanical computation. Their design philosophy centered on simplicity and raw processing power, with the main objective being to bring computational capabilities to a wider audience. The motivations then were primarily academic and industrial, aiming to unlock new possibilities in scientific research and business operations. Competition was nascent, largely defined by different approaches to achieving the same fundamental goals. As demand grew and applications became more sophisticated, the limitations of these early designs became apparent. The need for greater multitasking capability led to the introduction of multiple cores. This was a pivotal moment, allowing a single processing unit to handle several tasks concurrently, significantly improving the user experience for everyday computing. Each new model was designed to address the bottleneck of single-core processing, enabling smoother operation of multiple applications running simultaneously. The architects of these multi-core systems aimed to distribute the workload more effectively, ensuring that neither the central processing unit nor the main memory became overwhelmed. This was a direct response to the evolving landscape of software, which was increasingly designed to leverage parallel processing. The quest for speed then drove the increase in clock speeds. Higher clock frequencies meant that each core could execute instructions at a much faster rate. This advancement was crucial for applications that demanded rapid, sequential processing, such as gaming and complex simulations. The design compromise here often involved managing heat dissipation and power consumption, as higher speeds generated more thermal energy. The motivation for these speed increases was to provide a more responsive and dynamic computing environment where applications loaded faster and graphical elements rendered with greater fluidity. The competitive pressure was intensifying, with companies striving to offer the fastest-performing processing units on the market. The introduction of larger and faster cache memory layers represented another significant evolution. Cache acts as a buffer, storing frequently accessed data closer to the processing cores. This dramatically reduces the latency associated with retrieving information from main memory. The problem being solved here was the speed mismatch between the incredibly fast cores and the comparatively slower main memory. By bringing frequently used data closer, the processor could perform operations much more quickly, leading to noticeable improvements in overall system performance. This was a sophisticated engineering challenge, requiring careful consideration of cache size, associativity, and replacement policies, all aimed at maximizing hit rates and minimizing access times. Imagine your computer's brain, the processor, as a bustling workshop. Inside, there are dedicated workers called cores. Each core is like a skilled craftsman, capable of performing a specific task. The more cores a processor has, the more tasks it can juggle simultaneously. Think of a quad-core processor as having 4 craftsmen working at once, while an octa-core has 8. Now, these craftsmen don't just work alone. They can often multitask by splitting their attention, which is where threads come in. A thread is like a single instruction or a small sequence of tasks that a core can handle. If a core can handle multiple threads, it's like one craftsman expertly switching between 2 different projects, keeping busy even if one project has a brief waiting period. This makes the workshop feel even more efficient. The clock speed, measured in gigahertz, is like the pace at which these craftsmen work. A higher clock speed means each craftsman is moving faster, completing their individual tasks more quickly. So, a processor with a higher clock speed, all else being equal, will generally be faster at processing instructions. Different processor models are designed with various layouts or architectures to excel at different kinds of jobs. Some have many cores that are efficient at handling lots of simple tasks at once, perfect for tasks like browsing the web or running multiple applications. Others might have fewer but more powerful cores designed for demanding jobs like video editing or gaming where each individual task needs a lot of raw processing power. To keep these busy craftsmen working at peak performance, there's a special, super-fast storage area called cache memory. Think of it as a small workbench right next to each craftsman. Instead of having to walk across the entire workshop to fetch a tool or a piece of material from the main storage room, the main memory, they can grab what they need from their immediate workbench. Cache memory stores frequently use data and instructions, so the cores can access them almost instantly. This drastically reduces the time spent waiting, making the whole workshop run much smoother and faster. The way these processors are physically built, the manufacturing technology, also plays a huge role. This refers to the tiny size of the components on the chip. Smaller components allow more to fit on the same space and also use less energy and generate less heat. This is like making the tools and materials themselves more efficient. Processors built with newer, smaller manufacturing technologies are typically more power efficient, meaning they use less electricity and don't get as hot, which is especially important for portable devices. This advancement is a constant race to pack more power into smaller, more efficient packages. The latest generation of processing units, distinguished by their advanced manufacturing processes, are finding diverse and impactful applications across a wide spectrum of consumer and professional devices. For instance, the entry-level models, built on highly efficient architectures, are powering the next wave of everyday computing. In smartphones and tablets, they enable seamless multitasking, from navigating complex web pages and streaming high-definition video without lag, to running augmented reality filters that overlay digital information onto the real world. Every day, users experience tangible benefits like extended battery life, allowing them to stay connected and productive for longer periods without needing to recharge. These chips also make it possible for budget-friendly laptops to handle common tasks like document creation, online learning platforms, and casual gaming with surprising fluidity. Moving up the performance ladder, the mid-range processors are becoming the workhorses for creative professionals and serious hobbyists. Gamers benefit significantly, experiencing smoother frame rates and higher visual fidelity in popular titles like Cyberpunk 2077 and Elden Ring, which demand substantial graphical horsepower. Beyond entertainment, these chips are accelerating workflows in photo editing software such as Adobe Photoshop and Lightroom, allowing for faster application of complex filters and quicker export times. Video editors working with 1080p and even some 4K footage find these processors offer a noticeable improvement in timeline responsiveness and rendering speeds for projects involving multiple tracks and effects. At the pinnacle of the lineup, the flagship processors are redefining the boundaries of what's possible in high-performance computing. These are the engines driving cutting-edge workstations for demanding tasks. In the realm of video editing, professionals are now effortlessly handling 8K footage, performing real-time color grading, and rendering complex visual effects in applications like Adobe Premiere Pro and DaVinci Resolve with unprecedented speed. For 3D modelers and animators using software like Autodesk Maya or Blender, these processors significantly reduce rendering times, allowing for faster iteration and experimentation with intricate designs and simulations. Furthermore, their immense parallel processing capabilities are crucial for the advancement of artificial intelligence and machine learning. Researchers and developers are leveraging these chips for training deep neural networks, accelerating scientific simulations in fields like molecular dynamics and computational fluid dynamics, and powering sophisticated data analysis algorithms that were once computationally prohibitive. The tangible benefit here is the acceleration of discovery and innovation. The integration of this advanced processing architecture has profound social and economic ramifications. On the economic front, it fuels a productivity surge across industries. Businesses can now perform complex data analyses in minutes, not days, leading to more informed decision-making, optimized supply chains, and personalized customer experiences. This increased efficiency translates directly to economic growth, and the creation of new job roles centered around managing and leveraging these powerful computational capabilities. Socially, the benefits are equally compelling. In healthcare, for instance, accelerated drug discovery through intricate molecular simulations promises faster development of life-saving treatments and personalized medicine. Educational institutions can offer more engaging and interactive learning experiences, with simulations and virtual labs that were previously unimaginable becoming accessible to a wider student population. The entertainment sector, from realistic visual effects in films to immersive virtual reality experiences, is being revolutionized, offering new forms of creative expression and consumer engagement. However, the widespread adoption of these processors also raises significant concerns. The immense computational power required to train and operate complex artificial intelligence models necessitates substantial energy consumption. This has direct environmental implications, exacerbating the carbon footprint associated with digital infrastructure. Furthermore, the rapid pace of development often leads to a shorter lifespan for existing hardware, raising questions about planned obsolescence and the resulting electronic waste. The continuous cycle of upgrades, driven by the pursuit of ever greater performance, places a strain on both individual consumers and the planet. The ethical considerations are equally weighty. As artificial intelligence and high-performance computing become more pervasive, questions surrounding data privacy, algorithmic bias, and the potential for job displacement due to automation become increasingly urgent. Ensuring that these powerful tools are developed and deployed responsibly is paramount to mitigating negative societal impacts and fostering equitable progress. Despite these challenges, the potential for these processing advancements to democratize access to technology and reduce the digital divide remains a critical area of focus. By enabling more efficient cloud computing and remote processing, individuals and organizations in previously underserved regions can gain access to sophisticated analytical tools and digital resources without requiring massive local infrastructure investments. This opens doors for entrepreneurship education and access to essential services, bridging geographical and economic barriers. The development of more energy-efficient architectures, alongside advancements in renewable energy sources powering data centers, offers a path towards mitigating the environmental impact. The ongoing research into less resource-intensive AI training methodologies also holds promise. Ultimately, the ethical deployment of this transformative technology hinges on proactive societal dialogue, robust regulatory frameworks, and a collective commitment to harnessing its power for the benefit of all. The trajectory of processing units is poised for dramatic transformations, driven by a confluence of relentless innovation and emerging paradigms. Roadmaps indicate a continued push towards greater computational density and efficiency, with advancements in fabrication processes shrinking transistors to near-atomic scales. This miniaturization, powered by breakthroughs in nanotechnology, will unlock unprecedented performance gains and drastically reduce power consumption. Expect processors to become not just smaller and faster, but also inherently more capable of handling increasingly complex tasks. The integration of specialized coprocessors for AI and machine learning will become ubiquitous, allowing for real-time inference and training directly on devices, accelerating everything from personal assistants to autonomous systems. Artificial intelligence and machine learning are no longer just beneficiaries of advanced processing, they are becoming integral to their very design. Future chip architectures will be co-designed with AI, using machine learning algorithms to optimize performance, manage power distribution, and even predict and mitigate potential failures. This symbiotic relationship will lead to processors that are not only more powerful, but also more intelligent in how they operate, adapting dynamically to workloads and user demands. The design process itself will be revolutionized, with AI assisting in exploring vast design spaces and identifying novel solutions that human engineers might overlook. Looking further ahead, the specter of quantum computation looms, promising a revolution that dwarfs current advancements. While still in its nascent stages, quantum processors hold the potential to solve problems that are intractable for even the most powerful classical systems. applications in drug discovery, materials science, financial modeling, and cryptography could be fundamentally reshaped. The transition to a quantum-ready infrastructure will be a monumental undertaking, but the potential rewards are immense, ushering in an era of unprecedented scientific and technological progress. Beyond the quantum realm, new computing paradigms are emerging. Neuromorphic computing, inspired by the structure and function of the human brain, aims to create chips that process information in a fundamentally different, highly parallel, and energy-efficient manner. This could unlock new possibilities for AI that mimic biological learning and perception. Simultaneously, photonic computing, which utilizes light instead of electricity for data transmission and processing, offers the promise of dramatically higher speeds and lower energy consumption, potentially overcoming the physical limitations of electronic circuits. These diverse avenues of research paint a future where our computational tools are not just extensions of our current capabilities, but entirely new forms of intelligence. The horizon for processing units is being reshaped by several groundbreaking technological advancements. Foremost among these is the escalating sophistication of heterogeneous computing. This paradigm moves beyond the traditional monolithic processor, embracing a diverse array of specialized processing cores integrated onto a single chip. Imagine a central processing unit CPU handling general tasks, a graphics processing unit GPU, excelling at parallel visual computations, and dedicated AI accelerators efficiently powering machine learning algorithms, all working in concert. This division of labor allows each task to be executed by the most suitable processing element, dramatically boosting overall system performance and energy efficiency by avoiding the overhead of general-purpose units tackling highly specific workloads. Another transformative development is the integration of persistent memory. Unlike traditional volatile RAM that loses its data when power is cut, persistent memory retains information. This holds immense potential for accelerating system responsiveness. Booting up a device or launching complex applications could become nearly instantaneous, as the operating system and program data would remain accessible without the need for slow retrieval from slower storage devices. This seamless transition between powered-off and fully operational states promises a more fluid and immediate user experience, eliminating frustrating wait times and allowing for quicker access to critical information and functionality. The influence of cloud computing continues to expand, offering a dynamic extension of local processing power. By offloading computationally intensive tasks to vast data centers, even less powerful local devices can tap into immense processing capabilities. This democratizes access to high-performance computing, enabling sophisticated simulations, data analysis, and complex rendering on a much wider range of hardware. The cloud acts as an on-demand supercomputer accessible from virtually any internet-connected device, allowing for scalable solutions that adapt to fluctuating demands without requiring significant local infrastructure upgrades. Looking further ahead, radical shifts in materials science and manufacturing techniques are poised to redefine what is possible in processor design. The exploration of novel materials beyond silicon, such as advanced carbon-based compounds or exotic topological materials, could unlock unprecedented levels of electrical conductivity and thermal management. Coupled with innovative fabrication methods like atomic layer deposition and advanced lithography, these materials will pave the way for processors that are not only significantly faster and more energy efficient, but also remarkably smaller and more densely packed, pushing the boundaries of miniaturization and performance. The relentless evolution of processing units is profoundly reshaping numerous industrial landscapes, ushering in an era of unprecedented capabilities and innovations. In the realm of interactive entertainment, these advancements are the bedrock for truly immersive and lifelike gaming experiences. The sheer computational power available now allows for incredibly detailed graphics, complex physics simulations, and sophisticated artificial intelligence, creating virtual worlds that blur the lines between the digital and the real. Players can explore environments with astonishing fidelity, interact with characters possessing nuanced behaviors, and engage in gameplay that reacts dynamically to their every move. This leap in realism is not just about aesthetics, it's about crafting narratives and challenges that resonate on a deeper emotional level. Similarly, the motion picture industry is experiencing a dramatic acceleration thanks to these processing breakthroughs. Tasks that once consumed days or even weeks, such as intricate visual effects, rendering, and high-definition video editing, can now be accomplished in a fraction of the time. This allows filmmakers to iterate more rapidly on creative decisions, explore more ambitious visual concepts, and bring their visions to the screen with greater efficiency and cost-effectiveness. The ability to manipulate and composite vast amounts of visual data in near real-time empowers artists and directors to push the boundaries of storytelling through visual means, leading to more breathtaking and sophisticated cinematic achievements. The impact extends critically into the healthcare sector, where enhanced processing is revolutionizing diagnostics and treatment. Sophisticated algorithms, powered by immense computational strength, can analyze medical imagery with unparalleled precision, identifying subtle anomalies that might escape human observation. This leads to earlier and more accurate diagnoses of diseases, enabling prompt and more effective interventions. Furthermore, these processors are instrumental in developing personalized medicine, simulating drug interactions, and designing bespoke treatment plans tailored to an individual's genetic makeup and specific condition, ultimately improving patient outcomes and advancing the frontiers of medical science. The automotive industry is also undergoing a radical transformation, driven by the capabilities of modern processing. The development of fully autonomous vehicles relies heavily on the ability to process vast streams of data from an array of sensors, cameras, radar, LiDAR, in real time to perceive the environment, make critical decisions, and navigate safely. Beyond self-driving technology, these processors are enhancing advanced driver assistance systems, ADAS, providing features like adaptive cruise control, lane keeping assist, and automatic emergency braking. This integration of sophisticated computational power is creating vehicles that are not only safer and more convenient, but also fundamentally redefining the driving experience itself. The proliferation of advanced processing units has irrevocably altered the fabric of our daily existence, acting as the silent engine behind so many of the conveniences we now take for granted. In our pockets, these silicon brains are the core reason behind the astonishing leaps in smartphone performance. They enable the fluid multitasking, the near-instantaneous app launches, and the intricate visual processing required for high-definition displays and complex augmented reality experiences. This relentless refinement means our handheld companions are not just communication devices. They are powerful computational hubs, anticipating our needs and offering increasingly personalized interactions. Furthermore, this architectural evolution is the bedrock upon which lighter, sleeker, and more enduring laptops are built. Freed from the constraints of bulkier, power-hungry predecessors, these machines offer extended operating times on a single charge, liberating users from constant power outlet searches. This portability, combined with formidable processing capabilities, means that intensive creative work, detailed analysis, and immersive entertainment can now be conducted from virtually anywhere, blurring the lines between personal and professional spaces and transforming the very concept of a mobile office. The impact extends deeply into how we navigate our professional and academic lives. Complex simulations, data-intensive research, and collaborative virtual environments are no longer confined to specialized laboratories. Students can access vast educational resources with unparalleled ease, and professionals can engage in sophisticated problem-solving on the go. Entertainment, too, has been revolutionized with the ability to stream high-fidelity content, engage in complex gaming environments, and create multimedia projects with desktop-level power, all from increasingly compact and accessible devices. Our living spaces are also becoming more intelligent and responsive, thanks to the miniaturization and efficiency of these processing units. Smart home devices, from thermostats that learn our habits to lighting systems that adapt to our presence, are all powered by these sophisticated chips. This creates environments that are not only more comfortable and energy efficient, but also offer a new level of personalized automation. Similarly, wearable devices, once limited to basic fitness tracking, are now capable of sophisticated health monitoring, seamless communication, and intuitive user interfaces, all thanks to the relentless drive for smaller, more powerful, and more energy-efficient processing architectures. This pervasive integration fosters a more interconnected world, where information flows freely and our devices anticipate and respond to our needs with remarkable prescience, paving the way for a truly intelligent global ecosystem. The trajectory of processing units represents a monumental leap in the advancement of computational power, serving as the very engine that fuels innovation and fundamentally reshapes our digital existence. Their capacity for transformation is undeniable, and their influence on the future of computing is poised to grow exponentially. By comprehending the intricate details and distinctions between various models, we empower ourselves to make more judicious elections and fully harness the capabilities of this remarkable technology. May this exploration serve as an initial stepping stone into the boundless potential that these processing units unlock, igniting a deeper fascination with the technological advancements that are actively sculpting our tomorrow. This pervasive integration fosters a more interconnected world, where information flows freely and our devices anticipate and respond to our needs with remarkable prescience, paving the way for a truly intelligent global ecosystem. The advancements we've witnessed are not merely about speed or capacity. They represent a profound shift in how we interact with the very fabric of information. From seamlessly managing vast datasets that underpin scientific discovery to enabling real-time collaborative endeavors across continents, these core components are the unsung heroes of our increasingly digital lives. They have moved beyond mere tools, evolving into sophisticated partners that learn, adapt, and contribute to an ever-expanding network of intelligent systems. The ability to process increasingly complex instructions with unparalleled efficiency allows for the creation of experiences that were once confined to the realm of science fiction, from immersive virtual realities to predictive analytics that can address global challenges. The ongoing refinement of these computational heartbeats promises even more astonishing possibilities. We are on the cusp of breakthroughs that will redefine industries, accelerate medical research, and unlock new frontiers in human understanding. The continuous push for greater efficiency, reduced energy consumption, and enhanced parallel processing capabilities means that the applications for this technology will continue to expand in ways we can only begin to imagine. As these processors become more capable, the intelligence woven into our daily lives will deepen, leading to environments that are not just responsive, but actively anticipatory, making our interactions more intuitive and our lives more enriched. The journey of these processors is a testament to human ingenuity, a story of relentless progress that continues to unfold, promising a future where the boundaries of what is possible are constantly being redrawn. This ongoing evolution ensures that our digital landscapes will become increasingly sophisticated, dynamic, and responsive, creating a harmonious synergy between human endeavor and technological advancement.